Hello everyone, welcome to lecture 17. In this lecture, we're gonna talk about the two-dimensional flow in soils. Up to now, actually up to the lecture 16, we talked about the one-dimensional flow. So there's a one column and either you have a upward flow or the downward flow. So for the two-dimensional problem, let's think about this kind of setting that you have a dam and upstream there's a water level and downstream the water level, and there's a basement rock which is impermeable. And let's set the datum here, and the head difference between the upstream and downstream is about 10 meter. And here, yeah, this is about 2 meter. And then you can think of like the water flowing through the soil underneath the dam, and the flow line of the water going in and going out, you think about this whole subsurface, it will be something like this, right? So water will flow through this streamline. So then let's say that this is the point A, and maybe here is point B, and maybe here is point C. Then at A, elevation head is about 10 meter, and the pressure head is 0 because it's exposed to the atmosphere. Then the total head will be 10 plus 0, so it's a 10 meter, right? At B, so here, the total head will be the same, and elevation head is minus 2 meter because we set the datum here, and the pressure head will be what, 12 meter, so that the sum of these two becomes 10. At C here, because it's from, I think at the datum we have elevation head 0 and the pressure head 0, so total head is 0. So at C, the total head will be also 0 meter, right? And the elevation head is minus 2 meter, so pressure head is 2 meter, right? So then from B to C, from the water flowing from the location B to C, because of the friction while the water flows through the soil, total head will decrease because of the head loss. So we can think that from B to C, the HT decreases from 10 meter to 0 meter. Right? Then can we calculate the HT at a certain arbitrary point? For example, here, maybe here. So that will be the question of this class. So main question is, can we compute the total head at any location of interest? So if you think that this curved shape, a curved flow path as a straight line, we can maybe linearly delineate, interpolate the total head loss. So that's the basic concept of the Cpg flow analysis. So once we have the total head, then we can compute the pressure head based on the elevation head and pore water pressure. So then we can compute the effective stress. Also, if we know the head loss over a certain length, then we can compute the hydraulic gradient. So then, using the Darcy's law, KIA, because we can estimate the hydraulic gradient, we can also estimate the flow rate, even in this two-dimensional flow problem. Right. So it will all start from the Cpg theory. So let's look at what is the Cpg theory. So Cpg theory here starts from the Laplace equation, and in two-dimensional domain, water goes in horizontal direction, that's x direction, and y direction is the vertical direction, and q in x direction is the same with the q out, and also q in the y direction is the same with the q out in the y direction. So in 2D domain, the Laplace equation looks like this. So Kx is the horizontal permeability and Ky is vertical permeability, and Ht is the total head. So you can see that the total head gradient over x distance is the constant, because when you differentiate 2 times, then it becomes 0, which means that the gradient is constant. So if we simplify this two-dimensional problem into 1D case, so Kx equals to Ky and the dy is 0, then it will be just like this equation, so that this second term goes to 0. So then if we integrate 1 time, then the ht over round ht over round x is constant, which is hydraulic gradient. So this is just the same with Darcy's law. So then this kind of the Cpg theory, that the Laplace equation can be solved through various methods. One is that you can solve this partial differential equation directly, which will give the exact solution. And the second method is you can use the flow net. And flow net analysis, which is based on the graphical interpolation. And it also, this is a kind of graphical solution. And third is approximate solution, and fourth is you can solve this one numerically, either using finite element method or finite difference method. So objectives of the flow net analysis is to compute the pore pressure and effective stress for stability analysis, whether the soil will fail or not, or the structure will be failed or not, and to compute the flow rate, and to verify the piping condition and quick condition. So we're gonna examine the factor of safety against this piping or a quick condition. So flow net. Flow net is a network of flow lines and equipotential lines. And flow line, this is flow line. And when you see this figure, the flow line shows, let me use the blue one, represents the flow of water. So it should be a smooth curve, because the water tends to flow through showing a smooth streamline. And there's an equipotential line. Or lines. That's a contour of a constant total head. So here the red line is the equipotential lines. So along this equipotential line, one equipotential line, you have a constant head. So total head at this point, or this point, or this point, they're all the same. Maybe for this line, no, at any location, the total head will be the same. So basically the equipotential line shows the equipotential, so the total constant head lines. Flow channel. So flow channel is in between the flow lines. So here you have a flow line, and the second flow line, and third flow line, and the number of flow channel that we have here is this. This is the first one, and second, and third, and fourth. So we have 4 flow channels in this case. And in the flow net analysis, because we have a smooth streamline, and it's in the laminar condition, so there's no turbulent. So then there's no flow across the flow line. So the flow doesn't go this direction or this direction. So it will just follow this smooth line. Huh? Okay. So the flow net, so you have to be able to draw the flow net for a given configuration. And it's iterative graphic. So the rule number one is you have to maintain the normality, which means that the flow line meets an equipotential line at right angle, always has to be 90 degree. And the second is to maintain the square flow net. That means that the width for each element here, the width and the length are pretty much the same. So it will give you the square flow net. Let's look at the handout. If you go back in the lecture note, you'll find this handout. So seepage and flow net. The path taken by moving particles of water as they flow through a permeable material may be represented by a series of flow lines. And flow lines are nearly parallel curved lines since water tends to take the shortest path from point to point, but only to change direction in smooth curve. So it has to be smooth. And points of equal head of water, the equal total head of water on each flow line can be joined to give another series of curves known as equipotential lines. And these lines cross the flow lines at right angle. The pattern of approximate curvilinear squares formed by these lines is known as square flow net. So we just talked the length and the width in that element is they are similar to each other. To construct a flow net, a cross section of the site and structure is drawn to scale. So you have to have a CAD drawing that's drawn to scale to analyze the flow net. And then the boundary conditions are then examined, which means that whether it's this line is, for example, here, the wall is not permeable, so the water doesn't go into the wall, so it will be a permeable line. And also the bedrock at the bottom, it will have very low permeability, so the water doesn't flow through this impermeable stratum. That's the boundary condition. Normally, what you look for. The flow line starts and finishes at right angles to inlet and outlet surface. So here, this is the inlet, and it starts at right angle. And outlet, also it finishes at right angle. And equipotential lines start and finish at right angles to impermeable surfaces. So in this case, the equipotential line will start at the this wall, which is impermeable, and then also finish at the bottom strata that's impermeable. Thus, a few trial flow lines can be sketched in. These must be smooth curves. So you can kind of draw iteratively, and then you can fix it. And then if it doesn't look good, then you can try again. A few trial equipotential lines are then added to the diagram. These cross the flow lines at right angles, and the aim is to draw them so that the length and the width of the area enclosed by each intersecting adjacent pairs of lines are equal. So you're basically drawing the square flow net. This is unlikely to be achieved at the first attempt, but by gradual adjustment of the flow and equipotential lines, an accurate flow net can be drawn. So you have to try and to be also can use it. Okay, let's look at some example here. And when you look at the first drawing here, you can see that this is inlet and this will be the outlet, right? And the water doesn't flow because through the dam is kind of concrete. It looks like it's impermeable, and also you have impermeable rock. So I'll draw something like this. And Normally the flow lines less than 5. So number of flow lines you like to draw is less than 5. Maybe 3 or 4 is enough. And then once you draw this flow lines, then you can see maybe this is kind of symmetric, so you can have an equipotential line, and you can draw here, but this wouldn't make the square flow net. So I would draw somewhere here to make the element look square, and also here, so you can adjust the width of the equipotential line. And then you have a equipotential line like this. Then after you have this kind of a draft sketch, then you can adjust the this equipotential line and flow lines to be so that each other they can meet at right angle, and also making the the square flow net. Okay. Okay, this one we're gonna look at this one later, and then we'll come back to the lecture note here. So then let's assume that we have a perfect flow net drawn like this, and using this example, let's see how we can compute the flow rate and the pore water pressure and effective stress using this lecture 17 and the next lecture 18. So here, when you look at the configuration, it's a dam problem, and upstream the water height is 12.5 meter, and the downstream you have water depth is 0.5 meter, and let's set the datum at the low water surface in the downstream. And there's 2 flow lines, and 5 equipotential lines, and the saturated density of the soil is given as 2000 kilogram per cubic meter, and permeability is also given. So then you can define the number of channels. How many channels do we have? First one, and second one, and third one. So we have 3 channels, right? Okay, sorry. Let's use number of channel we should use is NF. So this is the symbol, and this will be 3. And number of equipotential drop, NE. How many drops do we have? From here, so this is the water inlet, and first drop, and second, third, fourth, fifth, and sixth. So we have 6 drops. Right? From inlet to outlet. Right? 1 drop, 2, 3, 4, 5, 6. And the total head difference between upstream and the downstream. That's delta capital H. And in this case, 12.5 minus 0.5, so it should be 12 meter. Right? And then the total head loss during the NE drop, so the equipotential drop, total equipotential drops is 6, right? Over the 6 drops, delta capital H is lost. And the small delta H is head loss per drop. So per each drop, we have 12 meter over 6, so we have 2 meter drops. Then you can also compute the I, which is hydraulic gradient. So for example here, if we know the B, and we know the head drop between C and D is delta small h, so then hydraulic gradient I will be delta H or delta small h over B. And for a single channel, we can use the Darcy's law. B times A is KIA, Kia, and here K is the soil property, and I is delta H over B, which is the length of each element, and then the A is the cross-sectional area, so A times 1.0 meter. So this here, the 1.0 meter, 1 meter is for unit length of a structure. So it kind of represents the 1 meter depth. So then, so K, here the delta H is what? Capital delta H over NE. I'm talking here. Then delta capital H over NE times A over B. And because that we drawn a square flow net, so from here, A and B are pretty much same. So then this can goes to 1. Okay. So the unit length of the dam, what we mean is that we can think of, let me draw this one. Think of the dam into this direction. And this is L, length of the dam. When you look at the 3D structure, then this L is 1 meter unit length. Okay, then for all channel, so here we look at only one channel here, but we have 3 channels, so you can compute the total flow rate by multiplying the number of channel to the small q. Then equation becomes like this. K times delta H, delta capital H times NF over NE times A over B. When it's square net, A will be the same with B. So you can eliminate this one. You can remove that. And the equation will be like this. So then what will be the unit? So unit here is meter per second is the permeability, right? The coefficient of permeability. And delta H is meter. And these two, number of flow channel and number of equipotential drop, doesn't have the unit. So meter square per second. And when you think about this, the flow rate should be the volume per time. So it's length cube over time, but it's for unit length of a dam. So here, kind of eliminate the length. It cancels 1, so that it becomes the power, right? So this one, in other words, you can say that the cubic meter per second per meter of a structure, per unit meter of the structure. If the dam length is L, then you can compute the total Q by multiplying the L to this Q. So then this will, it's gonna be the cubic meter per second. So for this configuration, the permeability is given. K is 10 to the negative 6 meter per second. And delta H is 12 meter. And number of equipotential drop is 6. And number of flow channel is 3. So then you can plug this number into here. Right? Then you can compute the Q. So per unit length of a dam, the flow rate will be 6 times 10 to the negative 6 cubic meter per second. If the dam length is 10 meter, then you can multiply 10 meter to this value. So then it's going to be 6 times 10 to the negative 5 cubic meter per second. Per minute, it's going to be, you can multiply 60 to here, right? 3.6 times 10 to the negative 3 cubic meter per minute. Okay. So then the last page of the handout here kind of shows how to sketch the flow net. So here we have a sheet piling that's blocking the water. And so you have a higher water level here, and this is a lower water level or when we can imagine that the water will go like this, right? So then how do we sketch the flow net? And this is gonna symmetry problem. So it's gonna be like this, when you do it. Step 1, consider boundary conditions of the flow region. So then this would be the inlet and this will be the outlet, and here is the impermeable line, and also this is the impermeable line. AB is the total head is constant, so AB is another equipotential line, and CD also the total here, total head is constant, so it's another equipotential line. And flow line should start at right angle from the equipotential line, so it's gonna be down, and then it goes up, down and goes up, and down and goes up. The shape must be kind of smooth. And then because you have a flow line that's intersecting the bedrock, so we have to adjust this line. And do we have that? Yeah. Here, do not construct too many flow lines. So typically 3 to 5 channels sufficient. So that means like 1, 2, 3, 4 will be enough. And because of this particular structure, the geometry, you cannot achieve the square flow net for the bottom here. So, but except for the bottom channel, you have a square flow net. So this is almost square, and this is almost square, right? This is almost square, but not this one. And then, how many equipotential drops do we have? From here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? So, the total head difference is 4 meter. Here the 4.5 and the 0.5, so the total head difference is 4 meter. And number of drops is 12. So then, or the ND or NE, either is fine. So then delta small h will be 4 meter over 12. And number of flow channel says first one, second one, third one, and fourth. So kind of it ignores the last one because it's too far here. It's not even touching the inlet surface. So I think this particular problem, you can ignore the last flow channel. In some cases, you can consider this one as like 0.2 or 0.3 channel. So maybe some people say that this could be 4.2, the number of flow channel is in this problem. But I think it won't make much difference. Okay, that's all for this lecture. Thank you.